Welcome to this lecture of Chemists for Future. In the next 30 minutes, I would like to discuss with you the role of light, daylight, visible light for sustainable chemistry. I'm a photochemist and I would like to first talk about the importance of light as an energy source and energy storage. And in the second part of my lecture, I would like to refer to the use of light in organic synthesis. Let's first have a look at the phenomenon light. Light comes in different frequencies and different wavelengths, and these are electromagnetic waves. And of course, we are talking here today about more or less the visible spectrum. So the daylight that we experience every day that comes to Earth from sun. And of course, it has different energies, blue and red colors in here. But when we look at the position here, it is between the UV and IR radiation on there. Overall, we have to say that visible light is not a very dense form in energy. When we look here at the sunlight spectrum that reaches the surface of the Earth, the majority is visible light, green and red light. Then there is a significant part of low energy infrared light, what we feel as heat. And there is a very small part of UV light that can burn our skin on there. So the visible light is indeed the majority of energy on there. Let's compare the density of light energy with the chemical bond strength. And you see here on the right-hand side, the energy of 1 Einstein, 1 mole of blue photons, green photons, and red photons, and in kilojoule per mole. And below here, you see some bond energies of chemical bonds. And a simple comparison shows you that the energy of a mole of green photons is only able to cleave very weak bonds in chemistry, like bromine-bromine or carbon-iodine bond. But a carbon-carbon or carbon-hydrogen bond is far out of reach on there, which is good news, because otherwise the visible light, the daylight that reaches Earth would start decomposing all organic matter right away. But I will come back to this a little later when we talk about utilizing visible light for organic synthesis. So here we conclude the visible light is not a very dense form of energy. So do we have overall enough energy from light on there? Let's do and follow a very quick comparison and estimation that was already more than 15 years ago published here by Dan Nocera. In 2001, the world consumed here 10 to the power of 20 joules or 13 terawatt hours in energy overall on there. And we expect this to rise on there. By 2050, we may even need up to 40 terawatt hours to power the world. If we would like to meet this demand from fossil resources, this is a very dangerous experiment because the CO2 levels will further rise, and we see how difficult the situation already now is. But this experiment, if we would like to match this energy demand, would be a very dangerous experiment because the CO2 level would rise higher than in the last 20 million years. Nuclear power can also probably not meet this demand of energy because every 2 days for the next 45 years, we have to open a new power plant to reach this power supply. And then there is the discussion using renewable resources for energy generation, plants, energy plants. But there, of course, we have this severe competition between food production. There is still hunger on this earth, food production and energy demand. When we look at the solar energy reaching Earth per hour, and here is the number, it's again a huge number, 10 to the power of 20 joule on there. The simple comparison of the numbers over here and this number shows you that what the Earth uses in energy per year comes from solar energy in 1 hour. So if we are able to harvest the solar energy input onto Earth of a few hours, then we can have enough energy for the whole year of the world on there. So in principle, there is enough energy. Where does current energy comes from? Just a quick look at the world energy supply. It's already a couple of years old, the data here, but the one thing we see immediately, the vast majority are fossil fuels, and this has to change. Globally, at 2016, only 2% were renewable resources. The situation is a little different in Germany. These are numbers from 2017. At that year, it was 12.5%. Now numbers have gone up, but the goal to be completely renewable in a very short time, in a decade or a bit more, is a challenging goal. So there's a lot of change that has to be done on there. The majority of all energy supplies, oil, coal, natural gas, and so on there, the majority is used for energy production, so heating, mobility, just energy that we need, electric current, and so on. And only a very small percentage of these materials go into chemistry on there. So the energy demand is indeed the key player when we talk about energy on there. So we've learned there is enough energy coming from the sunlight, and of course then secondary energy like wind, but we simply have to kind of harvest this and store this. Is this a new idea? No, it's not a new idea. We have to go back in time even more than 100 years, and then we will meet Giacomo Chamichan, an Italian scientist. He was working in Bologna in northern Italy, and he was very visionary because he discussed already more than 100 years ago that we should replace fossil fuels by visible light as an energy source and as a driver for organic synthesis and chemical synthesis on there. He published in 1912 a very interesting article with the vision of the future of photochemistry. And I really recommend reading this article on there. And here's a little text from this article. On the arid lands, there will spring up industrial colonies without smoke and without smokestacks. So his vision is that there is no combustion of fossil fuels on there. Forests of glass tubes will extend over plains and glass buildings will rise. Think about this, glass buildings in 1912. That was really a kind of a vision. So in these glass tubes, the photochemical process, which is the guarded secret of plants, will be mastered by human industry. So his vision is that we have an artificial photosynthesis as the source of the energy source for industry and production on there. So a very old idea is coming back on there. What are the challenges in solar energy fuel generation on there? We first have to concentrate the low energy density of daylight into high energy density of power and fuels. So it's a question of concentrating this. We have means to collect the energy by photovoltaics. We can convert light into electrical power by wind energy on there. The second challenge, of course, is the huge fluctuation in light and wind on there. So we have to store and to buffer the energy for times without light and wind. How can we store energy? There are options as potential energy. So we can just pump water up and let it down again, or pressurize things. But this, of course, to do this on a very large extent, it depends very much on the situation on there. It's very easy to pump water up if you have a mountain available and a lot of water on there. But in a country like Germany, that may be very difficult to store energy by this means to a very large extent on there. Electrochemical, we can store in batteries or in capacitors, and this is of course done, but very difficult to do this on a kind of global or on a country scale. Just think about how the battery for Europe should look like for all energy storage. Thermal energy storage, like say molten salt, so we heat something on there, that's also possible. But chemical energy storage is still a very important part. And as we will see soon, this is a way to store large amounts of energy for a long term. This is, by the way, again, a solution that nature has developed, because nature stores visible light energy by biological photosynthesis in chemical energy. So it upgrades molecules in their energy content on there. And how do we store energies in molecules? When we look here at simple one carbon molecules, there is carbon dioxide on the right-hand side. Then we have formic acid and methane here on the left-hand side. And you see the formal oxidation numbers of the central carbon atom. From methane to carbon dioxide, this is, of course, an oxidation. We oxidize the carbon atom, and this is always an exothermic reaction. And we know this, when you have methane gas and you ignite it, it burns, generates light and heat and carbon dioxide. But this also gives us already the blueprint how to store energy by chemical conversions. And this is reduction of carbon molecules. The reduction typically is energy consuming on there. So if we convert carbon dioxide into methane or into methanol or into other reduced forms of carbons, this is a chemical energy storage on there. So where can we store energy? In what kind of molecules? And here you have a comparison of the energy per unit weight per kilogram. So we would like to boil 10 liters of water, and the energy comes from different sources. So we can do this by electrical power that is stored in a high performance battery. But this battery will be rather heavy on there, no? It will be 4 kilograms. So a rather heavy battery, because the density of energy storage in a battery is not so high. When we compare this with petrol, or let's say methane, natural gas, you see that we only need 70 grams of methane. And if we burn this, so we release its energy content, we have enough energy to boil 10 liters of water. Even higher density comes with hydrogen, either liquid or pressurized. There we only need 30 grams of hydrogen. If we release hydrogen, so if we burn it with oxygen generating water and energy, this gives enough energy to boil 10 liters of water. So storing energy in chemical compounds is a very good way of high density energy storage. How do we do this? So sunlight is received by materials, and in the material we have charge separation. That is the trick to convert sunlight into a redox potential into an electrical potential. And this is what photovoltaic can do, or many other semiconductors, photosemiconductors can do. So the charge separation, so we are first neutral and we then separate into negative and positive charge, electrons and holes, and both of them can work. For example, the electrons can reduce a proton, and if we do this 2 times, we generate dihydrogen. The holes can oxidize water and generate the electrons that we need here for the reduction on the other side. In a bit more technical terms, photovoltaic can kind of pump the electrons to a reduction and to an oxidation to generate dihydrogen and oxygen on there in terms of a kind of electrolysis here, water splitting by photochemistry or photoelectrochemistry over here. A bit more advanced systems would be these kind of artificial leaves. So there are now technical solutions where we kind of mimic the biological photosynthesis in these kind of artificial leaves and use the charge separation for generation of dihydrogen and generation of oxygen here by water oxidation. So there are possibilities, technical possibilities to do this. There is enough energy around to kind of power the world, and the chemical storage of energy by solar fuels, artificial fuels, or high energy content chemicals like dihydrogen is a very important option for long-term and high-density energy storage on there. Let me now come to the second part of my lecture here, and this focuses on organic synthesis with light. We have seen that for chemical synthesis, only 3% of the overall global energy demand goes into the chemical synthesis and to make chemicals from carbon sources on there. Most of the carbon sources and resources of the fossil resources are used for the energy production. But why is it so interesting to do organic synthesis with light? So this is more or less the same picture as we have just seen this, but now the light should fuel a so-called photoredox catalysis. So we do have catalytic species that takes up the energy, harvests the energy from either sunlight, daylight, or visible light that we provide, and we do oxidation and reduction reactions. So we have chemical starting materials which are upgraded into chemical products of higher value on there by oxidation or reduction. So we use the visible light as a driving force for chemistry. When we look at chemical reactions, most chemical reactions, textbook reactions, have a kind of energy profile like this. We see the energy on the y-axis, and on the x-axis here, this is the so-called reaction coordinate. So it's like a little movie. We start with the starting materials, and then we kick off the reaction, and it runs to the chemical products on there. Typically, these starting materials will not react spontaneously, but they need a little kick to react. And this is what we're talking about, what we call the activation energy. We know this. If you have methane and you would like to burn it, you have to ignite it. So you have to give a little energy that then the reaction runs on there. And that's very typical for most reactions, for all exothermic reactions, organic reactions on there. And then there's, of course, the reactions that consume energy. And the classic example is the biological photosynthesis. So carbon dioxide is assimilated by plants, and with the help of sunlight and water and a complex photosynthesis apparatus in biology, the carbon dioxide is converted into organic compounds, fossil carbon resources on there. So in carbohydrates and all the organic material, our planet that is on our planet there. Where's photochemistry now comes into the game? We can imagine the following. We copy the principle of biological photosynthesis. So we have starting material that will not spontaneously react to chemical products because the chemical products are higher in energy. And so this is energetically impossible to convert them. And there is also an activation barrier to overcome. But with the help of light, it can be sunlight or artificial light, I come to this in a moment, we kind of lift the energy of our starting materials, and then we see it can go downhill in energy to produce the chemical products on there. Light is an ideal reagent for chemistry. Why is it so ideal? It provides the energy to drive reactions, and it's much better because it can be selectively applied to molecules. When you think of the typical way we start a chemical reaction, we just heat it. So you just heat all molecules and the solvent, so you apply very unspecifically thermal energy. This, of course, works. This is the basis for all our chemical production these days. But with light as a reagent, we can be more specific because the light goes directly to the molecule where it will be absorbed, or to a catalyst where it will be absorbed. We can use light in excess, and it leaves no trace, no? Because excess of light will simply just go away on there. And this is much better than using large excess of reagents. And all the chemists listening to this knows this: when you use a reagent in large excess in the workup, in the kind of purification of your products, this can be a very tedious thing to remove this and to purify. Visible light is very easy to generate. It comes for free as sunlight, but we can also generate by many light sources, converting electrical power into visible light. And visible light is safe and not toxic. So this is all very, very positive, using light as a reagent for chemistry, but the classic photochemistry until recently was not a very routine technique in the synthesis or even in chemical production. There were only a few products in chemical industry that were made by light energy input. Things have changed over the last 2 decades, and I would like to briefly explain why they have changed. These days, we do a lot of sensitized photochemistry. And sensitized photochemistry means that we are not putting the light energy directly in our starting material, in our organic molecule, because most of our organic starting materials are white. They will not absorb visible light. They only absorb UV light on there. To use visible light as an energy source, we then add a photosensitizer, so a second molecule that absorbs the light energy and then either transfers an electron to the substrate to activate or transfers the energy, so sensitizes this. We call this sensitized photochemistry, and we have to distinguish between the electron transfer, so that after light excitation, the photocatalyst, the sensitizer, gives or takes an electron. So this is redox chemistry, or the energy is transferred. And I will explain the principle of this just on the next slides. An ideal photoredox catalyst or sensitizer has several stable redox states and absorbs well in the visible range and has long-lived microsecond excited state. So the choice of material that we can use to harvest light energy and to transfer this energy then to chemicals, to organic molecules to react is rather wide, but we have to look for these specific properties. But you will see there are many examples already now. Let me briefly explain some basic photophysical principles. Just imagine, this is the photocatalyst and our sensitizer. This has absorbed the light energy. And the second one here, this is now my molecule that should react. This has not absorbed the light energy. So the energy must come from here to here. So how do we transfer energy between molecules? There are 3 different ways how we can do this. There is the so-called Förster resonance energy transfer, and I will briefly depict how this works. This is here my photocatalyst that had absorbed light. That's the donor of energy. If this has gone to any excited state, so it has taken the energy. And now it transfers the energy to my molecule that I would like to react, and this is the acceptor. So the donor goes back to the ground state, the acceptor molecule goes into an excited state in a higher energetic state and can react. This type of Förster resonance energy then transfer, this works over long distances on there, but it has also some limitations. For example, the kind of emitted light energy and the absorption of the acceptor should overlap. There's a second mechanism how we can do this, and this is called the Dexter energy transfer. And here something else happens. And just look at the principle. We simply exchange 2 electrons between the 2 molecules. I go back once more. So the donor, this is my photocatalyst that has absorbed energy, so it's in a higher energetic state. And to my second molecule, it gives 1 electron. At the same time, the molecule gives 1 electron back. So we stay neutral, but at the end, the molecule now is in a higher energetic state and can be then react further on. And the third option is the electron transfer. So we call this photo-induced electron transfer. And the photo-induced electron transfer uses the excited state of the photocatalyst. So the photocatalyst absorbs light energy. And now this photocatalyst has become a stronger oxidant and a stronger reductant. Let me briefly explain this, how this can happen. It's similar as in the photovoltaics, but now we are on a molecular basis. So the photocatalyst, after absorbing light energy, converts this light energy into redox power, so into the power to either accept or donate an electron. And this energy is simply added to the properties, the redox properties of our photocatalyst. So now the substrate over here, so my molecule I would like to react, can easily give one electron to the photoredox catalyst. And you see what is happening here now. It's a charge-separated state. And we have seen this before in photovoltaic materials on there, but now it's between two molecules in organic synthesis on there. The charge-separated state has generated a radical anion and a radical cation as the reactive species that now will undergo reactions. And there is one thing to briefly mention. These radical anion and radical cation, of course, can easily be combined or recombined if this electron here simply just go back here. And then you see what has happened. The absorbed light energy has been simply just converted into heat and without chemistry. So there's a trick. Nature also uses this, and chemists also use this widely, the so-called proton-coupled electron transfer. And you see what happens if after or simultaneous to the electron transfer I just explained, I transfer one proton back to the photocatalyst. This will neutralize the charges, and I have the diradical species that will undergo chemistry. I briefly explained that this all can be done by solar light, by sunlight on there. But different to solar fuel energy generation, this which only makes sense when we use natural daylight and sunlight, for chemical synthesis, it is quite often better to use an artificial light source. Why is this so? You do not want to have varying conditions in your chemical synthesis. The chemical synthesis, either in a research laboratory or in chemical industry, should be consistent every day. So the yield of a reaction or the molecule that I generate should be the same and in the same amount on a Monday, on a Tuesday, and on a Friday. When we would use natural irradiation, sunlight irradiation, we would depend on weather, and we would depend on the year and on the intensity. So the reaction would be much faster, let's say in a desert area in the Mediterranean, and much slower if we go to northern parts of Scandinavia. Therefore, it makes sense to use controlled conditions. So to take renewable energy, electric power, and convert it efficiently by light-emitting diodes into a specific visible light wavelength. And this is then used to drive chemistry. And I here show a few pictures how this can be done on small scale in the lab on there, but of course it can also be used on a larger scale. So here, for example, we can take an LED and wire this glass rod like a light guide. We bring the light energy into an organic reaction in a reaction solution. And there are ways to do this on much larger scales on there. Let's have a look again at the sunlight. You remember I was discussing that the light energy, the visible light energy, is not very dense. And we made this comparison that visible light photons are not able to cleave carbon-carbon-carbon hydrogen bonds. But this is organic synthesis to make and break covalent bonds in carbon molecules on there. So we have to find a trick how to do this. And the trick is very simple. Again, copied from nature. We use more photons. Nature uses 4 photons to split one molecule of water into oxygen and generate the electrons, ATP equivalents on there. So multi-photon chemistry. But how do we realize this? Nature does this very simple. We have antenna pigments, and the antenna pigments, so the the pigments that make the green color of leaves, they take the energy, and the energy is then transferred by the mechanisms I just explained, by energy transfer to a redox active part, which is not absorbing visible light. And this redox active part then does the redox chemistry, generating electron-rich compounds on there. How can we do technically processes by using more than one photon? And there are different ways how we can do this. There is the principle of two-photon excitation. This is widely used in analytical chemistry or in laser physics. So we can excite a molecule, and while it's in the excited state, we can excite it again by a second photon. These two-photon excitation is possible for certain molecules, but it always requires very, very, very high light intensities, much higher light intensities than we can typically generate with a simple LED light source or with sunlight. The reason for this is that the excited state here has only a very short lifetime, so it comes back to its ground state. And in this short lifetime, it has to be hit by a second photon. So the probability is not very high, and this requires then very high light intensity. Multi-photon processes are, of course, also known in semiconductor heterojunctions, so in photovoltaics. So we do have material that has a valence and a conducting band here, and this band gap here is the energy difference. So one material can absorb light, shuttle the electron to a second material, and can again absorb light. This is a very good principle for photovoltaics, so to convert light energy into electrical power. It is not so easy to use this in chemistry due to the instability of these materials, because chemical reactions can be proceed under very harsh conditions with highly reactive intermediates. There is a third possible way to do this that we term consecutive photoinduced electron transfer. So now we start again with a photocatalyst material. We excite it, and we do first an electron transfer from any kind of a donor, and we convert the photocatalyst into a radical anion. Visible light can now excite this intermediate by a second time on there, so we call this a doublet state on there. As this is a stable species, so we convert the photocatalyst into, you can call this a pre-catalyst, into the catalytic active species that is then excited. This principle works with low light energy intensities on there and allows to do chemical reactions with the harvesting and utilization of more than one photon. And one molecule that can do this is this one here, the rhodamine 6G. It's a red compound, it's a dye, an organic dye that can be subsequently excited, reduced, and again excited. What kind of chemistry can we do with this? For example, cross-coupling of heterocycles. So forming carbon-carbon bonds between, by activating a carbon-hydrogen and a carbon-bromine bond. This is a classic reaction in organic synthesis to assemble molecules in a very defined way. Classical methods use transition metals to do these coupling, but with the help of visible light, the rhodamine 6G, these reactions can also proceed simply by light activation. And you see here for the specialist among you some examples. Let me close with one specific chemical example, the chemical synthesis utilizing carbon dioxide. Of course, using carbon dioxide in chemical synthesis will not help us addressing climate change, because the amount of carbon dioxide we will use in chemical synthesis is simply not enough to take all the excess carbon dioxide out of the atmosphere. But imagine there is a chemical, maybe even industrial synthesis that uses as one starting material to make polymers, to make building materials, to whatever, to make chemicals that we use, and to use as one starting material carbon dioxide from the atmosphere. Again, it mimics the principle of biological photosynthesis. Biological photosynthesis takes all of its carbon starting materials out of the atmosphere on there. If we can mimic this, we can have an artificial photosynthesis in industrial production on there. Let's have a look at how we can realize this. And of course, these examples I'm now sharing are at the state of laboratory experiments or at academic research, and it will take some more time to transfer these reactions into industrial productions on there. But here we see a reaction that can utilize carbon dioxide, and I would call this really a kind of a dream reaction, because the carbon dioxide, and we have learned this is carbon in its lowest oxidation state. It's very unreactive on there, very low in energy. And what we do is we insert the whole molecule of carbon dioxide in a carbon-hydrogen bond of our starting material. So we are not doing synthesis only with carbon dioxide, but we use it as one reagent on there to make a carboxylic acid. And you see this principle works for quite a number of molecules. You can even make ibuprofen, which is an anti-pain drug on there, by this procedure inserting carbon dioxide. Again, I would like to emphasize using carbon dioxide in organic synthesis will not kind of take all the excess CO2 out of the atmosphere, but it is a contribution to a more sustainable industrial production, also using carbon dioxide as one of the starting material, like nature does in the biological photosynthesis on there. How does this work? Let me briefly explain how we can make this happen, this reaction. We start here with a molecule, organic molecule that can absorb light. We can excite the molecule by visible light, and in its excited state, we learned that this molecule can easily oxidize other molecules. And this is our second catalytic species we need here. It's a so-called thiol. This is oxidized while the photocatalyst is reduced. This thiol molecule here is then, after loss of a proton, has the properties of removing one hydrogen atom from the molecule. So we take out a whole hydrogen atom to close this catalytic cycle. This intermediate that we have generated here is now reduced by the reduced photocatalyst, resetting the photocatalyst on there. Overall, what have we done here? We have the CH bond in the molecule, and we have removed a proton. But we have removed the proton not as we typically do in chemistry by deprotonation using a strong base. We have removed the proton in two steps. Step number one, we take away a whole hydrogen atom. Step number two, we give back one electron. These two-step deprotonation leads to a carb anion, which is a very valuable intermediate in organic synthesis. And this right away in classic chemistry reacts with carbon dioxide and makes the carboxylic acid on there. We can do this chemistry also with aromatic CH bonds. So we start with an aromatic ring like naphthalene, and the CH bond here is, in the CH bond, we insert a carbon dioxide molecule to make in reasonable yields here these carboxylic acids. Here we use a quite interesting photocatalyst, and I would like to just briefly explain how this works. This is a photocatalyst, an organic molecule, an anionic organic molecule, which can be excited by visible light here, and then becomes a very strong reductant. This molecule now is able, so being an anionic molecule, is able after excitation to inject an electron into many molecules. So here I use the example of a benzothiophene as my starting material, but we can also use naphthalene or others, and we convert this into its radical anion. The radical anion intermediate can react with carbon dioxide, and after kind of deprotonation and reoxidation, we are generating the carboxylic acid on there. Still, these methods have limitations, but many molecules can be converted, and we hope that such principles can be further developed to make starting materials, for example, for polymer synthesis, where the carboxylic acids in a polyester or polyamide, the carboxylic acids are generated from CO2 incorporation into organic molecules. This brings me to the end. I hope I could show you that visible light is a very interesting source of energy. And to use this source of energy, which comes as daylight free to our planet, or can be generated very efficiently by modern artificial light sources. So to utilize and store this energy, we have to use chemistry. So we have to convert light energy into chemically stored energies. The technologies are there, but now they have to be implemented and further developed. But also in organic synthesis, light can do a lot, because light can enable us to do chemistry which is otherwise not possible. That is chemistry where the starting material have less energy than the products. So we do endothermic chemistry, so we upgrade the molecules in their energy content by additional light input. And this, in my opinion, has a lot of perspective for future processes for chemical production on there. And I'm pretty sure if we develop these things further, it will help us a lot in making chemical production more sustainable on there. It's a very important process to make chemical production more sustainable and to reach our sustainability goals on there. I would like to close with a quote I like here, that I have a strong belief that the very important next steps in sustainable chemistry is technology development. So we do have to find technical alternatives that are simply better than the current technical alternatives to overcome the use of fossil resources. And I think the technology, the ideas are there. They now have to be transferred into real technical solutions and then implemented in industry. Thank you very much for listening.